they work the way they do. Okay, cool. See if you don't fall over. Okay. So I think last time we stopped, let me make sure I remember what the last thing was we did. We talked about region models. We talked about some basic simplification of stuff. We haven't officially gotten to addition yet, although I showed a few things about addition. I think the very last thing I did, actually I'm not sure. What was the very last thing I did?
The region model.
The region model, okay. So, so real quick, what does it mean to reduce a fraction?
To simplify it to a smaller version.
And fundamentally, what are you doing when you do that? So if I have one that's almost too simple, you do not have to write it the way I'm about to write it. Because why is that one pretty simple to reduce? 5 goes into 15. I love it. So if you think about it real quick, and this is 1/3, correct?
Yes.
Because I divide by 5, divide by 5. If I drew 1/3, and then I broke that up. Now watch this, this is kind of cool. This is getting a little bit ahead because this is sort of getting into division territory, but if I broke this up into 5 parts, now how many little subregions are there? 15, and how many of them are shaded?
5.
So does everybody see what just happened? That means 1/3 is 5/15. Yes? So dividing the 5 out is taking away these kind of unnecessary cuts somebody made. Does that make sense? So 5/15, if I just took these cuts back, before you cut the brownies like that, when there was 3 giant brownies, 1/3 of them were still there, right?
Yeah.
Maybe. So it's, you know, we all know the algebra of it. You all maybe have done this before, right? We most of the time don't do this crazy thing. But that's really kind of useful for bigger numbers, and that's really useful if you're doing algebra with variable expressions. That's where things get really interesting. When you have to factor stuff, do you guys remember doing that? And then cancel shit, yeah. So you're nuts. Okay. But it's really cool. The visualization of what that means is really simple. Just take those cuts away, and then we're back to 1/3. Okay, like it. So what if I had something like 484 over, what do you got, Jeff? 680. How would you reduce that?
Probably like 2.
All right, so you could do divide by 2. So that would be what? 242 over
340.
340. And why did you say divided by 2? Because these are both even.
Yeah.
Did anyone else think about a bigger number that you could have divided first? 8 won't go in. 4 would definitely go in because the last 2 digits are divisible by 4. Bless you. But what am I going to do now? If I did this first, what am I going to do now? Divide by 2 again, which overall is 1 division by 4, right? So that's why when you reduce fractions, it doesn't really matter if you don't guess the right biggest number in the first place, because you're just going to keep going until you can't do it anymore. Divide by 2. Divide by 2. What do I get? 121. 170. I love it. Can anyone tell me what's the only number that goes into 121 besides 1 in itself? 11. And does 11 go into 170? No. What does that tell me? You're done, right? No number goes in the top and goes into the bottom, so you're done reducing. I love it. All right, so we all know how to reduce fractions. Even if they're big-ass things, you just do whatever you notice immediately. Because then you're going to make them smaller, and you keep going. Okay, so we know this stuff. No. Little. Here's something interesting. Is 3 11ths, is that equal to what, Jeff? 36 over 130. You get this right. Yeah. Seems right. Okay. I think that's right.
Yes.
Somebody sees what I'm trying to do. Sort of gave the game away. One way you could, what's one way you could check to see if this equality is true?
You can see how many times the top one is in the bottom.
So you could do what with this?
Divide.
Reduce it. If this reduces to this, then they're the equivalent fractions, right? But here's kind of a shortcut. What is 132 times 3?
396.
And what is 11 times 36?
396.
If the two fractions are equivalent, this cross multiplication thing will be true. How's that? You guys with me on that? This is kind of like a precursor to cross multiplying algebraic equations. You guys remember that? X over 7 equals 12 over 13. You cross multiply. Why does the equation stay same? Because this is true. Now, why the hell is this true? Let's prove this. Let's do everybody's favorite thing in the world besides maybe third favorite thing. Right? Word problems, fractions, proving shit. Let me write this as A over B. Woohoo! If that's equal to another fraction, that means this other one of them has to be able to reduce to be the other one, correct? Stay with me. Is that cool? Which means that this one has to be A times something over B times that same thing, right? As it turns out, this is 3 times 12 over 11 times 12. Do you see how 3 11ths is in here? Right? The 12s would cancel. You guys kind of. And what do you get when you cross multiply? What is A times B times N? Freaking A times B times N, or ABN, I like it. What is A times N times B? All right then. Okay, I like it. Hey, Mikey. Now, immediately after that, let me show you something nifty. I don't know if this is in the same, no, this is not in the same order, and I don't care. Here's something neat. So what if I put 5 sevenths and 11 sixteenths? Are those equivalent? And always do this. This is really important, believe it or not. How do you check to see if these are equal when you do 16 times 5? So always do this times this and put the answer here. What is 16 times 5?
80.
80. And 7 times 11?
7.
So are they equal?
No.
No, but here's what's really kick-ass cool. If you always bring this one here and that one there, then however this relationship is the same as this one. Bless you. So which one's bigger here? 80. Fine. So then that's true. That's some nifty shit right there.
That's very nice.
Very nifty. So that's kind of like the next step. So if they aren't equal, you still know something. You know which one's bigger, which one's smaller. That's kind of nifty. Okay. Now, so let me take a step back. I can't remember, I think I went out of order last time for my notes, so I might repeat some things, I don't know. We talked a little bit about mixed numbers, yes? Mixed numbers versus, what's the other form it could be in?
Improper.
Improper, I love it. Okay, right. And this is not like a battle of the ages, but which form to put it in. And we talked a little bit about why the conversion things that we do make sense, right? So just a quick reminder, tell me how I would make this into an improper fraction?
Multiply by 6 times 5 and then add 1.
I love it. And last time we talked about why that makes sense, why that actually works. And then how do I go backwards? If I had 11 over 6,
You do.
so you can either do it directly or you can break the top up like I did last time, but 6 goes into 11 once with 5 left over. 5 left over the 6. Hey. All right, let me stop. I know you guys know this. But last time we did talk about why these work, which I think sometimes teachers kind of skip over, which is bad.
Yeah.
Because students start getting this mindset of, all right, whatever my teacher says is true. It's like, come on, you gotta know why it's true. Did I talk about the fact that this notation, I think I did, that notation sucks? Why?
Looks
like
It looks like multiplication, because we so put in people's brains, when they're sitting next to each other, you multiply. But this definitely does not mean 1 times 5/6, because that would be less than 1. That doesn't make any sense. So what's in the middle is this. Okay. So I did talk about that. Good. Just to make sure. All right. So now, oh, good. Now here is a trippy side note. Yes.
Kind of random, but do you care if we do like a diagonal slash for like the fractions? Because I've had teachers in the past.
Oh,
who
like 5 and 1 6 like that.
Yeah.
Yeah.
That's cool.
Okay. But I've had teachers where they're like, you can't do diagonal, you can only do on top.
I don't
I didn't know
Yeah, me too.
Yeah, that's
Yeah.
silly, right? If you do in Microsoft Word, you get an equation editor. It has fractions that way or that way. They mean the same.
Yeah.
That's really weird that they didn't like the diagonal at all.
I
Okay.
think they thought it confused you because it wasn't right on top and right I don't know.
Maybe.
Yeah,
Alright.
they didn't let us do that, so I just wasn't sure. how
Or they
the
had a
difference
run-in
was.
with the diagonal somehow
Yeah.
earlier in life.
Diagonally.
Kind of strange. Okay. Yeah, they saw Harry Potter, they scared
Yep,
him.
yep.
Diagonal alley. Okay. Where was I going next? Oh yeah. So, all right. What do you guys think about this? So here is 3/5, and here is 4/5. Can anybody come up with a fraction that is in the middle of those? Do you all agree? How many numbers are in between 3/5 and 4/5?
A lot.
Thank you. An infinite number, actually. You tell me any two numbers that are different from each other, there's an infinite number of things between them. Let's not worry about that at the moment, right? Think about this for a second, for several seconds. Can you find any fraction that is in the middle? It doesn't have to be perfectly, but it could be perfectly in the middle. In fact, there is a nice way to find the one that's perfectly in the middle. You guys remember, or can you add them and then do what?
Just add them across
Well, if you add them, what do you get?
10, like, you add the top and the bottom, right?
Oh, I see. Now, that's
That-
funny. That's funny you're
was in
saying
the
this.
homework.
Okay.
I saw something like that where it was like in the middle.
That freaked me out for a second because to me, that fact that works is weird, and it's one that I don't think many people know. So let's do the more direct one, and then we'll come back to that one. What I could do, wouldn't this have been a lot easier if I had made that a 2?
Yeah.
Wouldn't that have been easier?
Yeah.
Damn it, Jeff, with this shit.
Yeah.
Because what would the answer be?
3.
3.
That would be one answer. There's still an infinite number of things in it. But I didn't do that, did I? Because I'm a math teacher. So what do? You make this into 6 tenths, and you make this into,
8/10.
and then what's right in the middle?
7 tenths.
7 tenths. Yeah. Do you understand how you could keep doing that forever? What's in between these? What would I make the bottom become?
16 tenths.
Yeah, you would make the bottom become, none of it, what would you make the bottom become? 20. So this would be 14/20ths, 16/20ths, so what's right in the middle of those two? 15/20s, which you can reduce then, but still.
Yeah.
Is that cool? So you could keep doing that forever, couldn't you? Forever. So how many numbers are in between these two? An infinite number, because I can keep cutting it in half forever. Okay. Sorry, did I? Yes.
I was just gonna say, so the method that I was doing, does that work all the time also?
Yes, so the method that the book shows is kind of an obscure method. I'm trying to remember now. We did this last time. I gotta remember. I don't know if I want to try to do the proof because I haven't looked at the proof in a minute. But if I'm given two fractions, A over B and C over D, the process, now this should bother you in a few different ways. But one process to find something in the middle of them is to straight up add like this. Does that grate on anybody's nerves in a way? Are you ever allowed to do that? So this isn't, if I wanted to add this to this, wouldn't I just do 3 + 4 over 5? I wouldn't add the bottoms also, yes? Okay, good, right? So that is really weird, right? Like one thing is, why the shit does that work? So if this is in the middle of these two, doesn't that mean that this is true? Right? And real quick, before I get too far away from this, again, the number we found, what was special about this number? Why is that a most special number that's in between these two? Because it's right in the middle. If we do this, what do we get for these numbers? 7/10. Well, in this case, it is the same thing, darn it.
It's the same thing.
It's because these numbers are symmetric and they're nice denominators. But this isn't always going to be the middle number. It's going to be a number in between.
It'll be in between, but not.
Yeah, it's guaranteed to be in between. It's not necessarily right in the middle. So real quick, I don't know if you're still with me. This is very obscure. I don't know if it's ever going to come up, but I just want to take just a quick second. If I prove this part, then you can do something similar for the other part. So let's see. How do I kind of check this? Don't I cross multiply?
Yeah.
Yep.
Yeah, AB plus AD, right? If I multiply that here, less than BA plus BC. And don't these cancel? So AD is less than BC, right? Which means, I forget what that means. This is the part that I should have looked at, but I won't. But there's a little step in there missing somewhere, but you can start here and prove that this is less. And then the same method you could prove that this is bigger in the same way. Okay, but again, I don't want to waste any more time with this because it's very obscure. It's very obscure. If I had to find something between two fractions, I would basically do this. Unless the bottoms were really gross. So like if I had to find a fraction between 7/17 and, what do you got, Jeff? 23 25ths, right? Do you want to do it this way? I wouldn't want to do it this way. You guys understand? Because you have to first make the bottoms the same before you can do it this way. But now I can just do somewhere in the middle, I don't know where, 7 plus 23 over 17 plus 25. Which reduces if we want to.
That's how it is.
Listen, anybody got their calculator out? Let's check this. What is 7 divided by 17? I know we haven't officially talked about decimals, but, you know.
0.41.
Second start?
0.41.
4-1. And what is 30 divided by 42? 5/7, so about
0.71.
1. And then 23 divided by 25 is 0.92. That is between those two, right? Okay. Just to kind of show you concrete what the shit's going on, does it make sense? That does end up between those two. Is it right in the middle of these two? No. So that's the point I was trying to make earlier. Okay. Maybe. So you will have to do that a couple times in the homework, but it's not like anywhere near the most important thing. It's kind of obscure. Okay. So let's officially get into something that I sort of already did with you a little bit. And that would be adding fractions. Now, so we could start off with something crazy simple, like what is 1/14 plus 9/14?
10/14?
Yeah, right. Why is it not 10/28?
Because it's the same denominator?
True, and I really want this, I desperately want this to make sense. How many 14ths do I have here?
1.
So I have 1/14. How many 14ths do I have there?
9.
So I have 10 what's?
14.
14ths. So if you put 10/28, and you'd be like, how did you get 10/28? I don't see any freaking 28s up there. Right? In fact, if I made them 28s, it would be 2 and 18. There would be 20/28. Anyway, it's much fun.
Yeah.
So this is 10/14ths, and then do you think that's acceptable?
No.
I love it.
5 7.
5 cents. Here comes 7. Okay, so that's pretty nice, right? So when the denominators are the same already, you're like, awesome, give me a bunch of those. Right? So let's see what you think. I'm going to give you one where the denominators are the same, right? Don't overthink it.
XC over Y.
Before I made this 10, what would have been over 14? How did I get 10? Because what did I do on the top? Didn't I do 1 plus 9?
Yeah.
And that's how I got 10? Right? So how do you write this? What goes over y?
X plus C.
Yes, if you put xc, then you're multiplying. Cool, okay. So if the denominators are the same and I'm adding, you just have to add the tops over the bottom. Done. So we all know when this gets disgusting. Yes? This gets disgusting when?
Different denominators.
The denominators are the same. Now, they don't automatically get disgusting. Would you say that this problem here is disgusting? What problem, Jeff? You can do it. There you go. Look at you writing shit. There it is, man. Is that disgusting?
No.
No, it's barely a problem, right? What's the quick fix on this one? Why is this one so simple?
Because you only have to change one.
I only have to change one. It becomes the other dude, right? So what do I do to this guy? Say what? Multiply by 3? Yeah, so I'm like unreducing if you want to get crazy. So I'm building it up, whatever you call it. All right, again, I know we all know this, we should know this, but I know also, I don't care what level of math I'm at, people have this general dislike of fractions, right? But I like to remind people that they're just like terms. When I'm adding, subtracting anything, I can only put them together if they're like terms. This is 2 of these plus 1 of those. I can't do shit with that. Now I got 2 of these plus 3 of these. Okay, now I can consolidate that, right? Okay, lock it. There you go, Jeff. So, okay, what about this guy? Let's see. What do you got, Jeff? Let me just focus on the bottom here. 1 over 144 plus, what do you got, buddy? Keep going. 7 over, let's do, 120. I love that. Look at that step. If you look at that step, 2 9s plus 1/3, and then the next problem. Sorry. You're not being graded, so it gives a shit. But I want to remind you something. What is LCD based on? Something we talked about before. LCD is based on what process?
LCM.
LCM, right? And I showed you, so here's how I handle fractions with bottoms that are kind of gross, right? Kind of too big to work on, right? Can you factor that?
Yeah.
And what's the big one? 144 is 12 times 12, right? And 12,
6 and 2.
all right, 6 times 2. So you get 3 times 2 times 2 times 3 times 2 times 2, and we can consolidate that 3 squared times 2 to the 4th, yes? And what's 120?
10 times 12.
10 times 12? I like it.
5 and 2.
5 times 2,
6 and 2.
6 times 2, so then you get 5 times 2 times 3 times 2 times 2, is that cool? Which is 5 times 3 times 2 cubed, okay. Now, if you look at these, compare them, what is this guy definitely missing that that guy has?
5.
He's missing a 5, so let's give him, holy crap. You're a bust, sorry. Let's give him a 5. Alright. Now, he's not missing anything else that guy's got, right? He's got more 3s and more 2s, so he's cool, he's set. He's happy. What is this guy missing that he's got?
2.
Yeah, so you see that? He's only got 1 3, and this guy has 2 3s. So I'm like, oh man, you got 2 waffle pieces and I only got 1, right? The ice cream thing, I don't know if you remember. Trying to make the ice cream the same so the kids don't yell at you. So give him a 3, give him a 3, right? What else does he need?
Another 2.
Another 2. Okay. So it's all about, so all it becomes is, if you break them all the way down, you can see what they have and which one's missing what. It's a much simpler process. Now, I would only do this for the bigger numbers, right? So let's see what we get. What's this going to be? This will be 5 over this.
360.
How much is it? Sorry?
360.
No. 620, I think. Is that right? 720? Is it 720?
720.
720. Do you guys see that? It'd be 5 times 2, 4 times 3. Right? Or you just do 5 times 144. And so aren't these the same? Didn't we force these to be the same? Right? Isn't that what we just did? We gave them what they were missing. So isn't this the same as this? Yes? 2 3s, 4 2s. 2 3s, 4 2s, and a 5, and a 5. So that's going to be 7 times 3 times 2? 42 over 720. And now we've created like terms. This is the whole reason LCD is so important. Is so I can add them together. Right? So what do I get?
47.
47, 720. I'm pretty sure 47 is prime. So that can't reduce no matter what 720. Well, I'm pretty sure 47 does not go into 720. I'm reasonably certain. You guys, did anybody ever learn this way to do fractions? Be honest with me. Does anyone like this way? If you don't like this way, no, this is beautiful. You don't have to do it. This is just one example. If you have another way you do fractions that you like better, please keep doing that shit. Teach your kids that way. I love it. Right? This is just another way that sometimes gets overlooked. So I just like to show this method. Okay. Blah, blah, blah. Oh, so let me do this. Okay, I'm on a good point to put this. Let me give you this insane handout. So much.
Did we start 6.2 today? Is that what this
Yeah,
is?
we just took a step into 16.
Oh, so last time was 6.
Here we go. Yes. did this one.
What about kind of the 5.2?
So let's see what all is on this crazy thing. So on one side where it says fractions on the top, very direct to the point title. Changing mixed number to improper, changing improper to mixed, reducing fractions. And then part D we haven't really gotten to yet, but multiplying fractions down there. On the other side, is what we just did basically, right? And I have a few examples of how that works. I like it. You guys with me? So real quick, you guys see the 3 problems on the bottom of the adding fractions with unlike denominators? Do those real quick. Either this method or whatever method you prefer that you know.
Is it in part C? Are those the ones that are given?
So the side that says adding fractions with unlike. Yes. I'd have broken a rule here with the book, but oh well. C looks like it's going to come out negative. I'll show you a bit of a shortcut also to the prime factor method. But the first one, easy, nice, right? Multiply this by
2.
2. So you get 10 plus 3 over 14, you get 13 fourteenths. Ta-boom. Which is nice and proper, right? So you could do the prime factorization, but can somebody tell me, can you just see what is the biggest number, what's the GCF, what's the biggest number they both share? You guys see that?
9.
9, right?
9 cross.
This is 9 times 5, this is 9 times 2. So that, if you can see it, if you can see the biggest number they both have, you can shortcut the method a bit. Because now I can see, I don't have to do the full prime factor trick. No, I know he's missing what?
A 2.
He's missing a 2. And he's missing 5. So I get 4 over 90 plus 35 over 90.
39.
Is that acceptable?
No.
Is it?
No.
Divide by 3.
By 3.
3, right? 3 plus 9 is 12, multiple of 3, 9 plus 0 is 9, multiple of 3, 3 goes in about
3.
cheeky ass. I like it. Okay. By the way, just notice this. A 7/18, is that bigger or smaller than half?
Small.
Why is it smaller? Because half would be what over 18? 9/18, right? That is less than half. 2/45 is really tiny. So if I add a half to this tiny ass number, will it get bigger than 1? No. Does that sort of make sense? So what I'm doing right now is just estimate. So my answer should not be bigger than 1 for one thing, right? So that makes sense. Okay. What about, who's got a different way to do these? Could you tell me real quick what your different way is? Or if you don't want to, that's fine. Nobody? Okay. Yes?
Well, I just find.
Like on this one. Did you do this one yet?
Yeah, I did. I just find it's kind of like your way, but without like writing it all out. I just find what number each, like the common denominator.
Okay.
code, and then
What
I
they already
just-
have in common?
Yeah, and then I just multiply it.
Alright, so you just don't write it down, but you kind of do this?
Yeah.
Okay. Bless you. And did you have a completed your voice sort of like that?
No, it was pretty similar. I think it was just the fact that you were factoring it out.
All the way down?
But,
Okay.
I mean, yeah, it's.
Because here, can anybody see what they have in common?
84.
6.
Or 6.
Right, it's the biggest number that they have in common. Yes? Now, real quick, let me show you. Again, alright, you gotta, when I do these weird little tangents things, this is all about number sense. So the more number sense you have, the more you can play with stuff. So let's say you thought it was 3. This is 3 times 4. This is 3 times 14. Do you see how 14 and 4 share a 2, obviously? Right? So you can actually make this, take a 2 here, 6 times 7, take a 2 there, 6 times 2. Now you found 6. Yeah? Okay, so if you can't quite see, you just take a guess what it is, and then you can kind of adjust it if it's not quite the biggest piece, right? And again, if you don't like anything that I'm doing up here and you have a totally different way to find LCD and it works, please keep doing that. As long as it's not pushing your freaking fraction button on your calculator. That's not good enough, right? So what's this guy need?
A 2.
He needs a 2. And this guy needs 7. So now they both end up with this on the bottom. And what is this? 2 times 42? 84. 35 over 84. So I did break a rule. Oh well. Because we officially haven't learned negative numbers yet, but you know. We don't know. Okay. So what will this be?
Negative 13.
I love it. And that's pretty much prime, I believe. Okay. So I don't know. I don't know if these will help you at all. I just thought it'd be nice to have sort of a quick place to look at. I do want to, let me see. There it is. Okay. I got there, okay, good. Oh, let's do a couple more things, and then I wanna do some more stuff with the manipulatives, just a few more things. Let's see if you guys remember this word. Do you think fraction addition is it closed? Who remembers what that means, closure?
That we wouldn't be able to get it, like, if there was not a value, it would not add up or subtract it.
So closure is if I have two whole numbers. If I add any two whole numbers, then the answer is a whole number. That means that set of whole numbers is closed under addition. But are the whole numbers closed under subtraction? Can you subtract two whole numbers and get an answer that's not a whole number? Yes.
Yes.
2 minus 7, right? So whole numbers are not closed over subtraction. So here, the way to ask yourself this is, if I add two fractions, must the answer be a fraction? And if you think no, give me an example.
Like if you add 2/5 plus 3/5,
Yes?
you'll have 5/5,
Which is a fraction.
but it's also 1. Yeah.
Over 1, which is a fraction. So remember, every whole number is a fraction, yes? Okay. But I like what you're thinking. That's the way to think. So what do you think then? If I add two fractions, the answer pretty much has to be a fraction, right? You can't add two fractions and get the square root of 2 or something, yes? If you can, you gotta show. And it's all built on the fact that what officially is a fraction? What's the only kind of number I can put here? Whole number. What's the only kind of number I can put there? That is not 0. Kick ass. Okay, I like it. So what about, now let's go through some more properties. This is so exciting. You always are like, when are we going to talk about the properties? Commutative property. Do you think that fraction addition is commutative? What the hell does that mean?
You can move it around.
Yeah. Now, do we know that whole numbers are commutative under addition?
Yeah.
Of course they are, right? So that means, recall, let me put this right here. This is kind of neat. Whole numbers, A plus B equals B plus A. Now that is groundbreaking. That's a TED Talk, right? Okay, well, yeah, okay. So we know this, yes? So how is that going to relate to what the hell I'm about to say? So to show that fractions are commutative, I would need A over C plus B over D. I would need to show that this is equal to B over D plus A over C, right? I wrote a little bit differently just because of what I wrote over there. Oh, Jeff, you silly person. Let's do this. I'm going to do this because any fractions I'm given, can I always find an LCD? Yes.
Yeah.
I always can find an LCD between any fractions. I don't care how big the bottoms are. In fact, your last ditch effort is just to multiply the two bottoms together. That will always give you a CD, a common denominator, not necessarily an LCD. But like denominator. Well, I said, what is A over C plus B over C? What is that? And what did we just say about A plus B? Isn't that the sum of two whole numbers? Aren't whole numbers closed? So the top is the sum of two whole numbers. So could I rewrite this as B plus A?
Yes.
Which is that? So I just showed that this equals that. Hey. Which is the way a lot of proofs work. You start on one side, then you go, bah, 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 bah. Oh, I got that one. All right. So you just show that E equals. So this is what I call fractions inherit commutative property from whole numbers. Because they end up being based on whole numbers. Because they end up being all about the tops, right? Okay, maybe. What else we got? What other properties?
Distributive.
Yeah, let's do associative next. And it works the same way as associative. Okay. So I'd have to show that A over B plus C over B plus D over B, and I have to show that that equals A over B plus C over B plus D over B, right? And again, if anybody's like, well, you're cheating, Jeff, you're making all the bottoms, whatever the bottoms were, I can make them all the same. So then I can just look at this. All right, is everybody cool? That's associative, is when parentheses get up and move. So I can do a very similar thing, couldn't I? What is this? And then what is this? This will be, and isn't this, right?
Yeah.
And isn't that? So again, like, so we start on one side and we got the other side, meaning that these two things are equal. Same idea. So again, we inherit associativity from whole numbers. I like it. We're not going to do distribution yet because we haven't really defined fraction multiplication. But you're right, we're going to eventually have to do that. And then one more thing we could do is related to addition. Identity, kick ass. And of course, what do you think the additive identity is for fractions? Right, is something I add to keep it the same? I love it. And we could even do this, couldn't we? Right, just to make it a fraction. A 0 or b is 0, as long as b is not 0, but we said that at the beginning, so we're good. Okay, you guys doing okay? So every time we talk about a new kind of group of numbers, we have to analyze what properties they have, right? Okay. Oh, okay. So let's do this. Before I do the fraction manipulative stuff, do you recall this? What would I ask you to do here, or what would you do here?
Associative numbers.
Sure. And what's the idea?
Complementary.
Sort of compatible, right?
Compatible.
But I know what you mean. Right, compatible numbers. Yes. You would do this and this because it makes 100. So what would you do here? You would say, what number is that, Jeff? Fair. Now that we know all the properties work, what would you add first and why?
3/7 and 4/7.
Because that makes
7/7.
a whole, right? So this would be 1. And how do I write plus 5/7?
Just 5/7.
Because, you know, I don't know. They could have done that on 420. Maybe they were
Yeah.
in a different realm and I came up with this and they're like, sounds good. I can understand that. Like poetry and mathematics make more sense if you're, anyway, that's it. Philosophers and poets and mathematicians, they're very similar in that respect. What was the last thing you wanted to do? Okay, before yeah, that's true. I'm not gonna do that yet. I wanna do this first. So, I don't know if this is your favorite part or your hated part or whatever, but shit and a half. This wants to be yours. Oh. Yeah.
That's for reading.
Oh, you get lots of it. Look at that. Was anybody not here last time? We did a little bit with these things. What did I read myself? What I want you to do, let me write it up on the board, and then I get set up. I want you to represent, see, I think everybody should have enough pieces. Tell me if you don't have enough pieces. 2 1/6 minus 1 5/6. Represent this. And then we'll talk about how to do this. I don't think we did this last time. The minus. Oh, yeah, we go. Oh, in the, on my office hours? Okay, just shoot me an email and remind me you're gonna be there. Oh, did I turn this
I
one
don't
on?
even know how to describe it.
Did everybody write this down? Because of course I wrote it where the screen's gonna be. Yeah. Good old Jeff planning ahead.
Oh. It's 1, 6, and 1, and 5, 6.
This should feel very familiar again with the base 3 pieces we were doing before, and the base 10 kind of stuff we were doing, especially the base 10 stuff. There we go. Because how am I going to, holy crap, how am I going to subtract 1 and 5, 6 from this?
Just break
Yeah,
down
exactly.
the whole-
So I'm going to have to, get here. All right, gonna have to break one of these down. Okay, Jeff. Oh, fumble fingers. So now that I've got that, this is basically the same thing. And you guys remember doing basically this with the base 10 pieces? We took like a flat and we broke it up into 10 longs, right? So that we had enough to take stuff away. So now I can subtract 1 and 5, 6, right? And I get 2, 6, 11, which is 1/3, it counts, right? So the nice thing you want to do, when you start building up, you first introduce fractions, they're gonna get used to the manipulatives that you're using. When you start doing higher order stuff, you can always remind them visually why reducing makes sense. 2, 6 is the same thing as 1/3, they're the same piece. Okay. So let's do this. Oh yeah, I got my little pieces of paper somebody left for me. Do 2 2/3 plus 1 2/3. Remember we did this.
Oh, what the heck?
Tell me if you don't have enough pieces. I think everybody should have. Now adding is nice, right? Because you sort of can just work, you just push them all together. But what happens, of course? Yeah. Make a whole one. There we go. So visually, it's very simple what happens. What's the answer?
4 and 1/3.
4 and 1/3. 11. Now, is everybody with that? That's pretty simple. And again, the work that we did with the base 10 pieces and the base 3 pieces a long time ago kind of gets us ready for this. Pulling them apart, putting stuff together. If I kind of take these away, what would a student possibly do if they had to do this with, not visually, but just directly? Well, how would they write the answer, do you think? What's 2 2/3 plus 1 2/3? Just do it directly. What do you get? What's 2 plus 1?
3 plus
3 and
4/3.
4/3. Now, what's wrong with that? Yeah, 4/3 is improper, right? So, what is one way you can show a student? First off, you could just tell them this is improper, so that's not good form. How would you work with this to get it into better form? Well, what could you do with that piece? Write it in what form? Mixed numbers, right?
Numbers.
So isn't this 3 plus 4/3? And what is 4/3? 1 and 1/3. So do you notice, see that 1? Isn't that when we took these 3 pieces
Yep.
and made it into 1? Isn't that exactly what's happening? We took 3/3 and made it into 1 whole. Okay. So you can you can always relate what you have to do computationally. Well, not always, but most of the time. You can relate what you have to do computationally to the manipulatives, to the visual. Right? And if I go back, so this would be 4 and 1/3, same answer we got. Visual.
Right.
What was the first problem again? It was 2 and 1/6?
6, 2 and 1/6, and 1 and 5/6.
Okay. So what we had to do here, we had to take one of these and break it down into 6 triangles, yes? So what would that look like computationally? This would be fractional borrowing. Real quick, why does something like this, let's make it a little more interesting, work when I borrow? What does 4 represent? 4 tens. So if I put a 3 there, I can put a 10 on 12. Okay, that's why borrowing works. We're just moving 10. It's like the compensation idea, right? So here, if I break this up into 1 and 1, what does 1 actually represent? What did we break it into, yes? 6/6, yes? So this would be 1 plus 6/6. And of course, plus the 1/6. This is 1 and 7/6 now. So this is what we did, visually this is what we did. We took one of the hexagons, broke it up into six triangles, and then we put the triangles, there were 7 of them total.
Yep.
So now I can subtract 1 and 5/6, and you can see directly, these cancel. 2, 6, 1/3 kick ass, right?
Yep.
Do you guys remember doing fractional borrowing? No?
Yep.
Does it make sense here?
Yeah.
Yes.
Because, in fact, will this always be 6/6? Why was it 6/6? Because there's a freaking 6 there. So whatever number that is, 1 can become that over itself. 1 can become anything over itself. It's always really helping out. So like if I had to do, what do you got you? 3 and 3/8 minus 1 and 7/8. Here's the direct way to do this. I would borrow 1, and 1 is also known as 8 over 8. So then I would just add 8 to this guy. Now, this looks so different, because what do we always do when we're borrowing with whole number subtraction? Aren't we always putting a 1 on the number? Because we're always taking 10. But here, I need to take so many 8s. So it's not, you're not always gonna it's not always gonna be like 13, you're not always taking 10. In this case, I'm taking 8 8s from one of these guys. Does that make sense?
So for example, if it was, the operation was, for example, 4 wholes and minus, 3/16. So that would make those wholes be 16/16.
Maybe. I lost the first part of what you said, sorry.
So like if you have like 3
3
minus,
yeah.
like if it's a whole
Oh, I see
number
what you mean. Yeah,
minus
yeah.
fraction.
I'm okay, beautiful.
Yeah.
You're like, all right, you're one step ahead of me.
Oh.
So I put down here the actual work you could show yourself. 3 is 2 plus 1. 1 is 8 over 8. And then these go together, make 11/8. Right? So then 2 minus 1 is 1. 11 minus 7 is 4. So 1.5. Woo! Kick ass. Now, what Juan is saying is the way I do these problems. But it gets a little weird. So if you don't like this method, obviously you never have to do it. I would not recommend showing this to a student who's first learning this, by the way. 3 minus 1 is 2. right? 3 minus 7 is -4. So I had 2 and -1/2. So what is a half below 2?
4.
What's that? 1/2 below 2.
1.5.
1.5. Same answer. So if I had $2
Oh, okay.
and you took half of $1 from me,
Yeah.
I have $1.50 left, right? 1.5. Yep. And again, that's a little weird, isn't it? That's the whole thing you're talking about, right? So you never have to do that way if you don't want to. And again, I wouldn't show students that because this is exceptionally strange notation right there. Let me think, was there? Well, no, I don't want to get into that yet. That's true. I was trying to think if there was more I wanted you to do with this. I don't think so. Here, do one more problem. 1/2 plus 2/3 plus 1 and what do you got, Jeff? 5, 6. What's up?
Price of price.
Now, there's a few, all right, does anyone, I don't know, did you just get it set up? Has anyone got an answer yet? Did you, what'd you get?
3.
3?
3.
Okay, now, how did you get that? What did you do? Hopefully you didn't just actually do it. Right. It's just copy.
So I just combined the shapes together.
Which shapes?
So like I combined 2 of the triangles with the blue ones. So 2, 1, 6 with the 2 thirds.
Oh, so, okay, so you took 2 of these with this?
Yeah, and I made
Okay,
it-
kick ass, because isn't this another kite, another rhombus?
Yeah.
So that's a 1/3 piece. I like it, and of course, what does that leave behind? All right, I'm showing off my, I wanna make something nifty there. And then what does that leave behind? What is this?
That's a half.
That's a half.
6.
And that goes out. Now, what this illustrates, and so the answer is 3, right? And you can kind of back it up by doing the work. Visually, now what would we have to do computationally to do this problem?
Find the lowest,
Find the LCD.
denominator, yeah.
And finding the LCD is equivalent to breaking everything here up into triangles, right? You guys with me? Because then it would be out of 6, right?
Yeah.
We didn't have to do that, did we? So this is interesting. There will be some problems where computationally it's actually more difficult. Here we can make whole shapes out of different pieces. We didn't have to break anything up, did we? I like it. So I mean, that's something that could be difficult for a student to understand, but it should be really, now if somebody says, why don't we just always do fractions with shapes, what would you tell that student? Some students like, why don't I just always have little shapes and just do fractions with shapes? And
A big number.
shit, yeah. If you have to do 1/80th, are you gonna have that sliver in your, and you're gonna be like, wait a minute, you have this pouch under your hand. Here's your 80th, all right. That would be insane. Okay. You just gotta be ready to, this gets the basic idea across. You immediately want them to start to get the connection between what we just do by hand, do computationally, but you're always gonna get somebody who's like, why can't we just keep doing this forever, or why can't, and that's the quickest explanation, is the bottoms are not always gonna be 2, 3, 6. Okay. I think that's that's all I want to do with those. Alright, not too bad, so that goes up. And then the last thing, did I ever? No. I really suck at doing that. Everybody's home, I'm sorry. Last thing for today. We'll get out a little bit early maybe, let's see. I should say last several things. So watch this. This is a lot like a problem we just did. But let's look at this a little bit differently. Actually, we're going to do something that we did physically too. Let me just throw this word at you and see what you think about this. I want you to do this problem using compensation. What is compensation? What does compensation mean in real life? Compensation means you get,
Giving something.
yeah, somebody loses something and the other person gains it, right? So either one of these, what would be a good thing for them to get?
1 extra third.
One more third, right? Either one. So I don't know, which one do you want to get something? Maybe this guy because he's got so little? Yeah. I'm gonna try to be nice. So I'm gonna break this up into 4 and 1/3 and 1/3. Right, it's the same thing. And this of course makes 4, right? And then that's easy. 8 and 1/3. Yeah. So the idea of compensation still works on fractions, right? The idea of compatible fractions we saw earlier, that still works. What about, let me see. So what do you guys, so there's something I could do here that would make this easier. There's actually 2 different things I could do. What really sucks about this problem? Why would this problem be easier? 10 and 1/6 minus 5. Why is that an easier problem? What is the answer to this? 5 and 1/6, right? Because I'm not subtracting some fractional part. So I just really have to look at the whole numbers and put that guy on. So here, this is just like in the wrong place, right? So you can actually do one of 2 things. I really want this to make sense. You remember how if you have a subtraction problem, that's the distance between the 2 numbers? So if you make one number grow, the other one has to grow by the same amount. This is called the equal additions method from before. So if I gave this guy how much more stuff? 5/6. And I give this guy 5/6, the answer stays the same because I just moved both numbers by the same amount, so they're still the same distance apart. I really want that. We've seen that earlier this semester. So this will be 10 and 5/6 minus 6. And now it's easy. So this is a method we used back with just whole numbers. So of course, whole numbers do inherit almost everything from, fractions inherit almost everything from whole numbers because they're based on whole numbers. Okay, 11. And then last thing, this is the actual, and of course, what's the answer here? I'm sorry. 4, 5, 6. 4, 5, 6. What did this mean? High and a low, 11, right? So what if I had, because you can make a different problem. 3 and 3/7 plus 9 and 1/15. How do you think you make a range estimate? What sucks about this problem? There's fractions, okay? Make the low one with no fractions, right? So what would the low be? 3 plus 9. 12. And then the high, you just bump it up to the next whole number. 4 plus 10, 14. Yeah. So a good guess would be 13, right? Because that's the extra thing I told you. You can just average those to get a decent good guess. Is that cool? Because don't those suck? Those problems. So an estimate might be good enough, right? Good enough for government work anyway. All right. And that's what I have. It's government. Okay, good, I told you, I'm gonna stick to my promise. That was the last thing, so we're out quite a decent amount early. Oh, yeah, let's do the same thing, if you guys could drop those off back here, that would be cool.